Welcome to this tutorial on the very first MCMC method known as Metropolis-Hastings. I will show you how this algorithm works and generates stationary Markov chains. On the way, I will hint at various challenges and limitations associated with this algorithm as well. That said, I am assuming that by now you have a decent understanding of Markov chains. More specifically, you should be comfortable with the notion of stationarity of Markov chains. I had shown you an example of Markov chain reaching the stationary distribution only after few iterations in my previous tutorial, and I had also talked about some constraints and requirements such as irreducibility that are necessary to achieve stationarity. Now, the big idea that we talked about in the last tutorial was that if somehow we can simulate, that is artificially create stationary Markov chains, then we have a way to apply law of large numbers and solve expectations. I have seen many people get uncomfortable with this idea or thought, and it is normal to be uncomfortable since it is not very intuitive at first to think in this direction. So one more time, let's say we have a parameter space. Parameter space means that there are many possible values of our parameter, and each of these possible values has its respective plausibility. We can also say we have a distribution of parameters. However, we do not know how to sample from this distribution so as to apply the law of large numbers. And this is where we want to leverage the Markov chain's property of stationarity. And once we have created a stationary Markov chain, we will run through it many times and record the samples. The number of samples that we will record per possible value of parameter will come out to be in accordance of their plausibility. And by doing this, we would have approximated the distribution of parameters in our Bayesian formulation, and more specifically, the posterior distribution. But how to create such an artificial Markov chain of the possible values of our parameter in Bayesian formulation is the big question we want to answer today. So without further ado, let's learn by working through a simple example. I'm going to use this target function as an example. This is a one-dimensional function created by mixing two Gaussian random variables. Gaussian variables here have equal contribution but have different mean values, and result is a multimodal function, that is, it has two peaks. Look at its functional form of how this function is created. I'm using the symbol f for this function, and our goal is to obtain the samples in accordance with this distribution function. Now let's make up the initial value. I say that the initial sample is the one with the value 0.6. This is how it will look on the plot. The dot is placed on x-axis at 0.6. Now, the first sample was easy as I made it up. But the tricky part is what would be the next sample. At this point, you should consider that since we want to make a Markov chain of our samples, the current sample, that is 0.6, does have a role to play. That is, a new sample should be influenced by this current sample. Now this new sample could be on the left of our current sample, or maybe it will be on the right. Maybe it will be closer to our sample, or maybe it will be away from it. So question is, how do we make this happen? And here is a simple idea. How about we add a random noise to our current sample? Something like this. Okay, let's make sense of it. This equation is suggesting that the value of x at t equals to 1 will be the value of x at t plus some value we get out of normal distribution whose mean is 0 and has some variance. The variance or standard deviation of the normal distribution in this context is acting as the maximum step size you would take in either direction. Now another way to write this equation is to reformulate it like this. Both of these formulations are identical. You can try it yourself by writing some code. Make sure that you have a fixed seed, and you will see that the values that you will get will be same. And given this new formulation, we can also see this as a conditional proposal distribution for the new value given the current value. If you recall, I had mentioned in my previous tutorials that one general theme in Monte Carlo methods is to sample from a proposal or proxy distribution and then have a criteria to accept it or reject it. This proposal distribution is generally represented using a symbol called Q. Let's run with this idea of proposal distribution with the step size of 0.4. Just to be clear, I am using here the standard deviation and not the variance. Let's draw the proposal distribution whose mean is 0.6 and standard deviation is 0.4. The proposal distribution here is the one in the yellow color. You can see that it is centered on the value 0.6. And we now sample from this proposal distribution. The new proposed sample is shown using the red color and its value is 1.2. Having this sample generated by the proposal function is fine, but really the big question to answer here is to decide if we should move to this sample or stay where we are currently at. The minimum we can do at this point is to evaluate the current and this new proposed value using the target function. We then obtain the ratio of these evaluations shown using the symbol alpha. So we have a new number now, alpha, yet we still do not know how to decide to move to this new sample location or stay where we are. And as it is quite often in Monte Carlo methods to make this decision, we make use of another random variable. However, this random variable will come from a standard uniform distribution. Therefore, the value of this new random variable indicated using the symbol U will be between 0 and 1. And now we create our criteria, which is if the value of alpha is more than U, then we decide to move to the new proposed value. And if it is not the case, then we stay where we are and discard the new proposed sample. Now in many books and articles, this is called acceptance criteria, but I like to call it a move criteria. So why do I prefer to call it a move criteria? So here is our current storage of samples. The only value in it, really the first value in it is 0.6, the one that I made it up. If we decide to move to the proposed value, then we would put its value in our storage as well. However, if we decide to not move to the proposed sample location, then we would put the current value in our storage. You see, even though you would not move to the new location, you would still record an entry in your storage. It would be again the current value. Essentially, you would store a copy of it. This is, by the way, also the difference from rejection sampling algorithm in terms of notion of acceptance and rejection. Check out my tutorial on rejection sampling if you are not familiar with it. And this is why I like to call it move criteria instead of acceptance criteria. And in this case, we decide to move to the new location. And it should have been intuitively clear that it would happen. Notice that the new sample was at a location of higher probability than the current location, and so the move will happen. And so we update our current value to 1.2. Okay, fine. Let's quickly do the steps one more time. Now that we have the algorithm written down. Our current value is 1.2. We sample from the proposed distribution whose mean is now 1.2 and the step size or the standard deviation is 0.4. We show this proposed sample in the red color. We evaluate this new proposed value using our target function. We have already the previous evaluation in our cache. And now we ask uniform distribution to give us the sample. We now compare alpha and the random variable from uniform distribution, that is U, to make the decision. And the decision is to move to the new proposed location. Again, because it was a higher probability place than the current location, so we would have definitely moved. The value at new location is now 1.5. Now I'm hoping you have not forgotten about transition matrices. You should recall that we were multiplying the initial state vector with transition matrix to reach to stationarity. Check out my tutorial on Markov chain if this sentence did not make sense. And here so far you do not see any matrix. And the reason is that the example that I used in previous tutorial on Markov chains, I had used the discrete random variable. And here the target function represents the continuous random variable. The proposal function that you see is kind of doing the job of a transition matrix, and in the context of MCMC methods, we call it transition kernel. So transition matrix is for discrete random variable and transition kernel is for continuous random variable. The algorithm so far can be seen as the transition kernel, as it is helping you transition from current state to the new state or keeping you where you are. Why is it called kernel? I generally joke with people that in science, when you do not know how to name something, you just simply call it a kernel. So don't worry about it. It's all I can tell you for now. Now, I let it run for quite some time to collect a lot of samples. And while it is doing it, let's discuss some more aspects. First and foremost, let's talk about what is the single most thing that influences this algorithm. Clearly, it must be the step size. If your step size is smaller than the chain will visit nearby areas. And it is possible that it may get stuck there. If the step size is large, then you would jump from one place to another. This means finding the step size is kind of important. In a way, it is the hyperparameter of your algorithm, of this algorithm. So that is one thing to worry about. Another thing to worry about is how many samples do we need? In other words, for how long should I repeat these steps? This is another difficult question to answer. And I will answer these questions and many more in the next few tutorials. But for now, just know that these are the serious challenges with this algorithm to generate the stationary Markov chain. But still, how do I know if the samples I am gathering really approximate this target distribution function? And one way to do so is to create a histogram using the samples recorded and see if the shape is same as that of our distribution function. So let's do that. Let me make space for the histogram of samples recorded in the previous run. You can see that the histogram is being built, and while it is doing that, let's worry a bit more. Worry about the situation when you do not know the functional form of your target function, which by the way is the case in the real world high dimensional functions. So making the histogram is not going to help in that situation, my friend. And one quick remedy that is generally used is that instead of creating one Markov chain and reusing the samples from it, you create many Markov chains. You just make sure that the initial point that you start from is different for all these chains. And since the process is a stochastic process, that is, it has randomness, if all the Markov chains that you will end up creating result in a similar looking histogram or histograms, then maybe that is the proof that you have the chains that have converged to the target distribution. So our histogram is here. You can see that for this toy example, indeed we managed to generate an artificial stationary chain that really is approximating our target function quite well. With this algorithm, that is the Metropolis algorithm, however, there is still no guarantee that you would have approximated the target distribution. The stuff that we have discussed so far, that is the Metropolis algorithm, came into existence because of this paper published in 1953, and these are the inventors of this algorithm. There are two married couples in this team, in case you are wondering. The same last names is not a coincidence here. There are two more people who indirectly influenced the invention of MCMC method, this method. On the left is Stan Ulam and on the right is John von Neumann. And I had talked about them in my previous tutorial on sampling methods and had told you the story of how Monte Carlo was assigned to the class of algorithms that rely on random numbers. All these people used to work in Los Alamos in New Mexico, where atom bomb was invented. And also note the paper, note the title of the paper. If you pay attention, it is taking pride in state estimation, but more specifically using computer. They're calling it fast computing machines, but interestingly here we are talking about the very first primitive computers. They're talking about a computer called MANIAC, designed by Metropolis, and is shown here in the background. Seems Metropolis was quite creative with naming things. He was also the one to suggest the name Monte Carlo to Stan Ullum, and he named his computer MANIAC. It's actually an acronym that stands for Mathematical Analyzer, Numerical Integrator, and Automatic Computer Model. This is brilliant if you think about it. So the algorithm is named after Metropolis, whose name is the first in the paper, but it still does not necessarily reflect that the major contributions came from him. There is really no way of knowing. And to be fair, I'm not suggesting that it was not the case. Metropolis was brilliant, and it is possible that all these ideas were his. However, I want to talk about and celebrate one very important member of this team of inventors, and she is none other than Arianna Rosenbluth. She was a gifted person who had obtained her PhD at the age of 21 and was the one who implemented this very first MCMC algorithm on this primitive computer. This is a recent picture. She passed away recently in December of 2020 at the age of 93 because of COVID complications. And I feel connected to her somehow, and possibly because of my love for writing softwares. I love many areas of science and mathematics as such, and I generally tell people that I yet have to find a subject that does not interest me. But if I were to select one that is my most favorite thing to do, it would be programming, and my love for writing high performance and elegant code. I've been writing software for now over 25 years and have enjoyed every single moment of it. And more importantly, I highly appreciate the effort it takes to transform a concept, an idea, an algorithm to something that runs on computing devices. Whether these devices are computers at very big scale or they are resource constrained devices. And here is this grandmom who did that in late 1940s and early 50s on primitive machines. She must have faced the challenges we can't even think of. And hence I have this great admiration and love and respect for her. An article was recently published about her, and I'm sharing its link in the description. So please do use the link to read more about her and her life. So this was a little detour, and we need to get back to our subject to uncover some more mysteries related to Metropolis algorithm. Okay, back to our example. The first thing I want you to pay attention to is this ratio, that is ratio of evaluation of new proposed state and evaluation of current state, the alpha. By the way, this alpha is also called acceptance probability in many books and articles. And here I want you to appreciate that so far we have sampled from the proposal distribution, but we have not taken into consideration the probability of sample from proposal distribution's view. We have evaluated these samples using our target function, but we have not evaluated them using the proposal distribution. And this is where I introduce you to a more general and enhanced form of this thingy, the thingy being the acceptance probability that does consider the proposal distribution. This additional ratio that has now emerged in the alpha is called Hastings ratio, named after the scientist who came up with this form of the algorithm. Hastings published his great work on this subject in 1970, almost 2 decades after the original paper by Metropolis and team. Not only he generalized this formulation by introducing this additional component, but he also emphasized on the application of this algorithm in a variety of domains. He also provided the proofs and mathematical justifications. In many ways, he deserved the credit to popularize this algorithm as well. That said, the algorithm gained more attention in early 90s, especially when computing resources start to get cheaper. Now, if you have a proposal distribution that is symmetric, that is, probability of going from state to new state is same as that of going from new state to old state, then you can see that this component will be equal to 1 and will vanish. and hence Metropolis-Hastings version is seen as a more general form of the invention by Metropolis, the Rosenbluths, and the Tellers. I also want to show you all this in the context of posterior distribution so that you do not feel limited by the toy example here. So this is our posterior distribution formulation from previous tutorials. You also know about the troublemaker, that is the normalizing constant, and it translates into an intractable integral. Now the function f that I have used in the example represents the numerator, that is the product of the likelihood and prior. For the requirements of this algorithm, we do not need to know the functional form of product of likelihood and prior. All we need to do is to just evaluate it. We also do not need the denominator, that is the troublemaker. And you can see that since we use ratios, the normalizing constant will cancel each other. Now the significance of this algorithm is paramount. And it even earned its place in top 10 algorithms of the 20th century. Look at the algorithms along with whom it gets its place. I hope this helps you appreciate the number of domains and the applications on which this algorithm must have had its impact. And in this tutorial so far, I have addressed two main areas. I have explained what is it that we are chasing. We know that stationary Markov chains can let us visit states in accordance of their plausibility. So what we want is an algorithm that helps us create a simulated stationary Markov chain whose states are the values from our parameter space. And then we can apply the law of large numbers. Then I did the how part as well. That is an explanation of how such an algorithm to generate Markov chains work using an example. But we haven't talked about why this algorithm can generate the stationary Markov chain. There are two ways to think about this thought. The first one is to argue that the experiments show that this algorithm works. And I give you that, no problem, why not? I'm okay with that. And the second one is to prove it using reasoning and mathematics. But today I'm not going to walk you through the proof. Rather, I am providing the reference to the best explanation and proof I have seen. These are very well written 2 pages. Yep, just 2 pages. And no, there are no scary looking equations. You just require a bit of a patience and curiosity and application of rules of probability. More importantly, I promise that you will have a smile on your face as you will go through it if you do decide to do it. Also, I am providing some references to various blogs and papers that you should read on this subject as well. One blog is that of an MCMC expert. His name is Colin Carroll. He's an engineer working at Google these days and is an expert of MCMC methods. The example function that I used comes from his blog post. I also took the inspiration from the visualization that he had created and added my little twist and animation on it. You will find the example code in his notebook, whose link is in the description. But really, I would suggest to read his other blog posts as well and check out his GitHub repositories. You would find that his content is really lovely. I sure do. I love his content. And this brings us to the end of our tutorial. This was the first MCMC algorithm, and even though on the way I hinted at some problems, limitations of this algorithm, here I am showing them formally and adding few more questions and thoughts. These limitations do have remedies, and we will discuss them as we will progress through some more versions of these MCMC algorithms. I want to once again mention Miss Arianna Rosenbluth, the star programmer who made it happen, and pay my respect to all these people from days past for their significant contribution to science. With this, I end the tutorial for today. I hope this was helpful and useful. Please let me know in comments if you have questions and need clarifications. I thank you for the time you have spent here and wish you good luck with your learnings. Thank you. Goodbye. Bye-bye.